Let's start. All right. We are now venturing into calculus. This, to me, is the bread and butter of the course. It is 3/4 of your potential exam next year will revolve around calculus. So the better you know and understand calculus, the better for you. Most students will understand the first bits of what I'm going to teach you. So pretty much this week and next week, the basic skills of calculus most students will learn. It's the understanding of what calculus is used for and how to use it is what you're trying to learn. Okay, that's the harder bit. Let's start here. 16C. What do you need to know in 16C? Just this term. Average rate of change. Why is my pen not working? Give me a second. Is it recording? Yeah, it's okay. All right. Shh. Eyes and ears towards the board. Thank you. Listening. 16C, you just need to understand a couple of terms. Average rate of change. 16D is to understand the difference between average rate of change and instantaneous rate of change. What are they? In a nutshell, average rate of change is kind of like just the gradient. It's another word for the gradient. Now let's remind ourselves of how to find the gradient. Do you remember back in year 9? Gradient M is equal to y2 minus y1 over x2 minus x1, right? What is this describing? See, if you want to think about it, average rate of change, we're just simply saying, what is the change from one coordinate to the next coordinate and then one point to the next coordinate on average? So here's an example just to illustrate my point. When you first did quadratics, I can give you a graph that looks like this. Goes from here, touches there, comes back here, right? Let's say this is how long it takes you to get how many hours you haven't eaten, all right? So let's say hours, how many hours you haven't eaten. And let's say this is your wakefulness. So obviously, the more it goes up, the more you're wakeful, right? So at the start, when you first started starving yourself, you're okay. As you start starving yourself a bit longer, so let's say 5 hours, your wakefulness starts to get lower because you're hungry, you're drowsy, you're tired. But then as you increase and you start to fast crazily, and let's say you hit, 24 hours, now you're in this buzz. You're just crazy. You're just so hungry, you don't know what to do, you're frustrated, and so you're a bit more awake than usual. I'm just making it up, okay? So the scenario, this is the graph. If I asked you, what is the average, rate of your wakefulness? We can talk about from 5 hours to, let's just change it to 10 actually. 10 is just a nice double. 5 to 10. I'll do another line. So between 5 and 10 hours of not eating, 5 to 10 hours of not eating, how long is that duration? 5 hours. Now, how did you know that? You did 10 minus 5 on the x-axis. Okay, so someone said, I asked, how long is that duration of you starving? Just between 5 and 10. Yeah, that's 5 hours difference. Yeah? So you'd say, well, out of 5 hours, what is the change in your wakefulness? So what if I said your wakefulness was, you are now at 10% of your usual performance of wakefulness, versus now you are at 110% of your wakefulness. Then from 5 to 10, you went from 10% to 110%. What's that change? 100%. So you've actually increased from here to here. And overall, you made 100% change. Okay, there was a change of 100%. From the bottom part, after 5 hours, you're at your lowest point. After 10 hours, you're at your highest point. But you see, if we actually had to work out your actual change, each change is slightly different from here to here to here. Your performance is not constant. Your performance is squaring itself until it gets to 100%. But on average, over the 5 hours, okay, so how did I know it was 5? I did 10 take away 5. Then I took your maximum, your final performance, and your initial performance. Okay, so let's write down what you're saying here. We did your final performance, which is 110%, minus your initial performance, which was 10%, over what your final performance was after 10 hours, and then your initial performance was after 5 hours. This gives me, when you work it out, this is 100% change for every 5 hours, based on this gradient. What that line is telling you, that if I was working between 5 and 10, the rate that I'm going at, the rate of change, is that every 5 hours, you have an increase of 100% wakefulness. Does that make more sense? So it means, if I'd made a prediction, 5, 10, 15 hours to 20 hours, if you knew the rate from 5 to 10 on average overall was you were increasing by 100% wakefulness, then by the time, technically, the prediction is by the time you get to 15 hours of starving, you're now at another 100% wakefulness. So that's 200%. Then by the time you get to 20 hours, because we're saying every 5 hours there's an increase of 100% wakefulness, that's 300%. What we're studying when we say average rate of change is that no matter how the graph changes, because that's the thing about life, everything goes up and down, things change, but we want to know on average what you get. That's what you do. Let's say for your sacks this year, you would have had a good sack, you would have had a bad sack, but overall, what's your average? And what you would have done is you would have done, take all your sacks, add them together, and then divide it by the finals, yeah? But if you only had 2 points, if you took your first sack and your sack now, your latest sack, we found the average, how we would have done it is, how long did it take you between those 2 sacks? And then what's the difference between the 2 scores? That line that we're talking about is your rate of change. Does that make sense? Yeah, I'll draw the picture out again, just to illustrate to you. Let's use the sack idea. I think the sack idea might be more relevant. Let's say your first sack in this year was what? Was it linear? First sack was linear equations. I think on average, you guys were maybe hitting, that was I think 55 or 60, let's say 60%. Yeah? Then our latest sack, we did circular functions and exponentials. This is unit 2 now. How many months has it been? Let's say this was in, I think it was in March. We're now in September. How many months is that? Is it 6, 7 months? 3 plus, yeah, you're right, 6 months. So in 6 months, so if I now want to see the average, your first score and your final score. Now, we don't know your final scores yet. I've actually got 5 students to mark left over. But I would say there was a drastic improvement compared to the very first sack you had. Let's say you had a prediction that you had 80% on the sack. What we can say is that, what was the rate of change? What's the average rate of change? We only took your first one and your last one. You changed from 60 to 80. What's the change there? 20. But how did you know it was 20? You would have done 80% take away 60% over the duration that it took. So from March, that's 3 months of the 12 years. September is 9 months, the 9th month of the 12 years. So 9 take away 3 gives you 6 months. So 9 take away 3. And what this answer tells me, when you write 20 over 6, it means that if I just took that as a snapshot of what your growth is over this year, is I would say, on average, you are increasing 20% on performance on your sacks every 6 months. So I expect that by the end of this year, let's say assume another 6 months, if you were getting 80% on average, my prediction is you're getting closer to 100. Does that make sense? That's why we call the language average rate of change, because what we're doing is we're just taking one variable, which is time, performance. The other one was performance and time again, same thing. Yeah, I was just talking about wakefulness. So, in a nutshell, if that didn't really make sense, I was just trying to relate back. Why do we say in 16C, average rate of change, why does that mean the gradient? And what is the gradient really doing? So I'm trying to break it apart so you understand that you're just looking between 2 points in time and you're saying, what's the growth? And that growth is not very reliable, but it gives you a general prediction, okay? Because we know that life changes very consistently, yeah? All right, so 16C, you're just going to practice using the gradient. So every time they say find the average rate of change, you are going to find the gradient between 2 points. Now write this down as part of your notes. Gradient between 2 points. I've already bolded it for you, but I want you to write it down too to remind yourself, because it has to be between 2 points. So when we say average rate of change, notice before I had a final and I had an initial. So in order to find an average rate of change, you always have to find it between 2 points. Okay? Here's an example. Example 8 of your textbook. Here's your graph. That could be the reality of what your performance is every day. And they will say, find the average rate of change of the function shown in the graph. And notice the interval from -2 to 5. Okay? Now we know that from -2, 4, so -2, 4, I'll just draw a picture here. So when this is -2 and this is 4, all the way to, let's say, this point here is 5, and that's 20, we can see that the change changes very incrementally different. But if I wanted just to look overall, I'd be looking at from this point to this point, your initial to your final. Yeah? So initial to final. What is the average rate of change? That's what it's asking. Does that make sense? Okay, so how do you find the average rate of change? Again, I'm asking, what is M? What is the gradient? So in this scenario, y2 minus y1 over x2 minus x1, what would I be subtracting? Can I please have Artie? What would I be subtracting?
20 minus 4.
20 minus 4, so the y values first, 20 minus 4.
5 minus 2.
Good, 5 minus -2. Okay, so we're just doing y1 take y2, x1 take y x2, or whatever number you want to call it. Okay, and that gives you an answer of 20 minus 4, which is 16. 5 take away -2 becomes +2, so it's 16 on 7. What this basically means, based on the scenario, if we're talking about, well, time doesn't make sense because it has to be 0 onwards, but it's just saying for every 7 across, you're increasing by 16 on average. On average, this is increasing by 16 for every 7 across. That's what it's saying. Okay? All right. That is 16C. So when you do 16C, you're finding the gradient between 2 points. This was an example. Versus the next exercise, 16D. What is 16D? 16D is really what they're trying to get you to learn in calculus. This is what you need to understand. Instantaneous rate of change, instead of average, means between initial and final. Instantaneous means at one instant or at a particular point. So what does this mean? This is the gradient of a line at, fill this in, 1. Really key word. What is the difference between the two? Average rate of change means find the gradient between 2 points. So they have to give you a range or domain. Instantaneous rate of change, which is really the study of calculus, and it's the introduction to it, is how do you find the rate of change at that very specific moment? Okay, so what are we saying? So 16D, you can only estimate the gradient at the moment because you haven't learnt the theory of calculus yet. What we're saying is, in this graph, hypothetically, this is average rate of change. Instantaneous rate of change is asking this. At this particular point, sorry, let me do it again. When x equals to -2, what is the gradient at that exact point? So you see the difference? One is the gradient at exactly one point, which is the tangent line. It's the tangent line, so the line that touches the curve only once on the surface. What is the gradient? And if you think about like when you're driving a car, the moment you step on the accelerator, it had to have gone at an acceleration and then it starts to plateau because you keep the speed the same. So right there, at that particular point, what is your acceleration? And then how it changes over time. Each point has a different gradient. So every single point will have a different instantaneous gradient. Now what's the problem that you guys should be able to see already? When you're finding gradient, what's the formula again? y2 minus y1 over, and here's the problem. Gradient relies on the fact that you need minimum 2 points. That's the reality since year 9. Year 9 taught you that the only way to find the rate of change between one point to another point is you need 2 points to do that. So how do you do it if you only have 1 point? And it seems impossible to do. And that's what calculus is. The theory I'm going to teach you today, 17A, addresses this problem. And that's what you study. All those rules that you're going to be learning is to simply find the gradient at 1 point. If there was anything to take out of calculus, was that line. That understanding that calculus, the technique, all those things that you're going to learn formula-wise is to find the gradient at 1 point. Not 2 points, but at 1 point. So given any point, any x value, you are able to use these rules, your calculators, to find the gradient, the rate of change, for every single moment of that graph. That's what you're doing. So far, so good? Okay, so I'm going to zoom out and just get you to see the bigger picture. Average rate of change, year 9 stuff. That's your y2 minus y1, so 16C. 16D, okay, you're trying to find the gradient at 1 point. Now the only way to do it in 16D is you estimate from the graph. You kind of look at it and say, yeah, it's roughly, how much across and how much up. We're not doing that. We're going to move into 17A where I actually show you algebraically where the theory comes. So what I want you to practice, 16C, don't do 16D. Okay, listen to what I just said. Do 16C, don't do 16D. Okay, you just need to understand what instantaneous rate of change meant. Okay, now we do the theory. Here we go. Flip over to the next page. Flip over, actually not, is it here? Find the gradient. Yeah, okay, all right. Let's flip over to the next page. Does it start here or does it start there? Okay, yeah, we'll start here. All right, sorry, flip back. This is 17A. So what I want to teach you today is how to find instantaneous rate of change without estimating, because that's what 16D is. 16D says, all right, we can't find the gradient because we need 2 points, but if we had 1 point, let's estimate what it roughly would be, right? So you draw the line of best fit and you kind of guess what the gradient should be. We're not going to do guessing, we're going to do some algebra. Here's the logic. Let's do some logic. Let's say I want you to find the gradient of a tangent line. So I'm going to draw a line, the instantaneous rate of change, at x equals 2. So where's x equal 2? Here's 1. Here's 2. So what I'm saying is at this particular point on the graph, I want to know the tangent line, so this tangent line that touches, I want to know y equals mx plus c. I want to know what is the gradient. Okay, I want to know what the gradient is. That's called the instantaneous rate of change. That gradient at that particular point is the instantaneous rate of change. Okay, so That's instantaneous. So this is how the theory works in 17A that you need to learn and understand. And you only need to understand it in year 11. If you don't understand the theory that I'm talking about, you can memorize the rules, but it does help you to see the bigger picture as to why it works. So this is what they did. They said, all right, I want to know the gradient of this point, right? I only got 1 point. Now let's work out what that point should be. If this equation is x squared, y equals x squared, when x is 2, what's the y value here? 4. Very good. This is 2. This must be 4. How do I know? Because f of 2, when x is 2, you'll get 2 squared gives you 4. So the point is 2, 4. So I only got 1 point so far. They've only given us 1. So we only got 1 point. What's the problem with finding the gradient? I need 2 points. So what they say is, all right, well, let's do a hypothetical. Let's pick a second random point, right? Let's pick this point up here. Now that point, I chose that one specifically because it kind of aligns with the next number, which is 3. Okay? So the next number is going to be 3. Now if I asked you, at x equals to 3, what would the y value be? It would be 9. So this would be 9. So this point here would be 3, 9. So if I picked a random point, so I'm going to write here, pick random second point. And I chose x equals 3, so then f of 3 gave me 9. So here's my second random point, 3, 9. Now if I found the gradient for that, on a hypothetical sense, m equals 2, y2 minus y1, you would say 9 minus 4, and then 3 minus 2. Right, so you'd say, if I pick those 2 points, the average rate of change from 2, 4 to 3, 9, it's gone up by, from 4 to 9 is 5, and it's gone across by 1. Right, so you would say 5 over 1. Here's my question. So I'm going to draw that line. So here's your average rate of change. That's the one I made up. I made up a point. I said, let's pick x equals 3. Is the gradient of the black line the same as the blue line, which is the one I want? No. Can you see that? Can you see that because I chose 3, on the red line, on the graph, if I drew the average rate of change, yes, I've got a gradient, but the gradient is not truly accurate, is it? So the question is, how do I make it more accurate? How do I get it better? Because obviously if I chose 5, it would have been even steeper, right? It would have been higher. So how do I make it a bit flatter? Because right now my black line is too steep. How do I make it just a bit closer to the blue line? Anyone have a clue? So now we're thinking, and I love this. Can you do 2.1? And yes, you can. Let's do it. Now, this is where you have to do a bit of hypothetical thinking. If I chose 2.1, and you look at the graph, can you see that if I found the gradient of these 2 points, it's actually getting even closer to the blue line. But then what's a better point to choose than 2.1? 2.01. And what's a better point if I were to choose one to get it even closer to the blue line than 2.01? 2.001. Now what am I trying to guide you to? What's the best answer here? 2.0000001. Right? Because it's infinitely really close to 2, but not 2. So what they say is, this is the theory. Now I'm going to show you the formula. Don't get freaked out yet. But the theory that you guys just came up with, that's really good, that you're understanding where they're coming from. This is what they say. This is the formula they've given you. Now that looks scary. I'll guide you through it. This is what they did. They simply said, okay, so you got the 1 point. So sorry, flip over just to see my illustration here. You got 1 point. Second point. The second point is they say 2 plus h. What's h? H is that little extra that you guys said. So Milena said before, can you have 2.1? And I said, yeah, that you can. In fact, that was a better one than choosing 3. Then I said, what's a better one than that? You guys said 2.01. I said, okay, what's a better one than that? You said 2.0001. The pattern is, whatever that h is, that is infinitely small is what we want. But it's not equal to 0. It's just 2 plus this really, really small number. Now, if I asked you, how do you find the y value then? If x is 2 plus h, what would the y value be? How do I find it out? So before I said 3 and you said 9, and then if we did 2.1, we would have been 2.1 squared to get the y value. Then how do you do it if it's 2 plus h? H plus 2, missing something? Squared. Because all you're doing is the function was, if f of x was equal to x squared, if it was 3, you said 3 squared. So then if it's 2 plus h, you sub 2 plus h in and you get 2 plus h squared to get the y value. So far so good? So what I'm saying is that means the coordinate for your second point, they gave a formula for it and they said, well, what if it's 2 plus h? H is a very, very small number that you can come up with. And that means the y value is substitute 2 plus h in. But that really just gives you 2 plus h squared. So far so good? Okay. Now, if this is true, that's my first point, that's my second point. How do you find the gradient? y2 minus y1, x2 minus x1. Let's follow that formula that we just got. So here's my x1, here's my y1, here's my x2, the random point you guys made up before, and here's my y2. So if we write it all together, this is what you should get. y2 is 2 plus h squared minus y1, which is 2, divided by, divided by 4, minus 4, divided by 2 plus h minus 2. You following what I'm doing? y2 minus y1, that's there. x2 minus x1 is there. That's my first point, that's my second point. Can you already see something beautiful in the denominator? What's nice?
You just get h.
You just get h, which is why the formula in the first principles, that's why it's always h. Because the reality is you're always so close to the initial point, that initial points are going to cancel out. That's the reality. That's why you're correct. This will always be cancelled out. Now we can actually work this one out. Let's expand this. Let's expand the equation. Now you learnt from start of this year. What's the quick way of expanding 2 plus h squared? What does that give you? 4, yes, 4 plus. So square the first, remember the rule, a squared plus 2ab plus b squared. You get 4 plus 4h plus h squared minus 4. And what do you see again? What's beautiful? Which one cancels out? Very good. 4 take away 4 cancels out. And look at how beautiful this is. Because you end up with 4 times h plus h squared all over h. This is your gradient. Right? This is what the... Wait, am I missing something? Wait, let me just double check again. Wait, something's weird. Oh, no. Wait. Yes, it's beautiful. It's good. All right. We can simplify this further. What does that simplify to? Anyone notice? Because one of the things that I'll mention about later, this is going to be part of the exercise 17A, but just for now, what can you cancel out? H's. You can take out h as a common factor, h, you got 4 plus h divided by h, and h divided by h is 1. What does this imply? You got 4 plus h. Now, what was h again? An infinitely small number. Let's think about it for a moment. Let's just zoom out and think about what we said before. I said we had 1 point, 2, 4. I said pick a second point, and I came up with 3. I said choose x equals 3. And then I said, can we make it better for the average rate of change to be better? Milena said 2.1, so it's 2 plus a 0.1. Then I said, can you make it better than that? You guys said 2.01. And then I said, all right, well, let's make it, what's a better one than that? And you said, it will be 2.00001. So h is just this little extra infinitely small number. So then if that's true, that's x, then the y value is just take that x value and sub it in. So we get this y value, 2 plus h squared. If I put it into the gradient formula with 2 random points, and remember they're not equal, they're just infinitely really close to each other. If we solve for the gradient, you actually ended up with 4 plus h. But you just told me h is infinitely small. So if I asked you, what is the gradient equal to? 4 plus a very, 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 very small number, what does it tend towards? 4. So the gradient, if I wanted to know what is the gradient at this one point, my best estimate is going to be 4. Does that make sense? Because this bit here was key. Because you're taking 4 plus a very, 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 very small number. And this theory, we are now able to find the gradient of 1 point. And the gradient of the 1 point here would tell me this y equals mx plus c line, we've just figured out the rate of change here, m, best estimate is 4. And what that implies is, at that particular point, it is currently, for everyone across, it's going to go up by 4. That's the rate of this tangent, the green line that I've drawn here. That's the instantaneous rate of change. But you see, 17A, wasn't that scary? It's a lot of algebra, a little bit thinking, a little hypothetical. That last bit there, if h is infinitely small, then 4 plus something very, 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 very small is approaching 4. And so with that idea, this is what we call first principles. All the formulas you're going to learn in calculus, there's like 6 of them, you're going to learn how to find the gradient using only 1 point of different functions. You'll have x squared functions, you'll have sine x functions, you'll have cos functions, because the one I gave to you was an x squared function, right? There are different rules because someone out there, the mathematicians, have used this formula and then condensed it for you. They've already condensed it. And there are 6 common ones that you're going to learn. That's what most students do. But you can't take away the idea that the idea in calculus is really just finding the gradient of a tangent line at 1 point. That is literally the essence. If you had to take out chapter 17 in calculus, that's what you're doing. All the formulas from here is just to help you figure out, what if it's not an x grade graph? What if it's a sine graph? What if it's a log graph? What if it's an exponential graph? Then how do you find the gradient of each one differently? And all they've done is they've gone through all these rules, first principles, and they've condensed it to a nice, simple rule. So an example to quickly introduce to you, they use this formula to figure out what's a quick way to find the gradient of any point you want. So the one I wanted was at 2, 4. Instead of doing what we just did, there is a rule called the power rule, which we're learning next session. And this is how the power rule works, in a nutshell. The power rule works by dropping the power down. So if I drop the power down, and then minus 1 to the power, what does that give me? 2 minus 1. Very good. So drop the 2 down. So 2 comes to the front. And then what's 2 minus 1? 1. This rule, I'll do it again. What if I gave you x cubed? So the rule says drop down the power and then minus the power by 1. What do you get? 3. So x power of 2. Can you see the pattern? Drop down to 3 minus the power by 1. This is the formula to find the instantaneous rate of change at any point. So let's say we have an example. See how I gave you this one before? Instead of doing what we just did, you can actually get the answer of 4 very quickly. This is what you do. Since the derivative or the gradient is equal to 2x at x equals 2, because we're saying I want at the point x equals 2, notice the rule. M equals to 2 times 2. Wasn't that much quicker? I'll just zoom out and just talk about it again. The power rule tells you, and you're going to learn this next session, don't worry about it, I'm just showing you how much quicker it was. We didn't have to go through all of this to get the answer of 4. I did it in 1-2 steps. That's what you're learning. In chapter 17, you're learning rules. If you had an x squared graph, the power rule says drop down to 2 minus power by 1, and I get 2x. All I did was I just subbed in x 1 point. All I needed was 1 point. Now I was able to work out the gradient. This is one of the first exercises you're going to be learning for next time. Okay, but 17a, what do you want to take out of it? 17a, I'm going to get you to practice doing this bit. That's what you're practicing. If you're wondering what this rule is, let's break it apart. Here we go. Final parts of our video for today. I want you to have a look at this and break it apart. What's f of x plus h? That's your y2. That's the 2 plus h that you said before. You said pick a number, a random point, so that you get the y value for it. So that's my random point. Why is it h on the bottom? Anthony said before, the h's, the minus the x's, and you get h left over. So here, that's your y2. This is your y1. That's your original function at the particular point that you're interested in. And what's lim h approach 0? This is a fancy way of saying the limit as h gets infinitely small. Because that's what I was saying before. I said you started with 2, and Melina came up with the idea was 2.1. I said make a better number. You said 2.01. So you just made h smaller and smaller. So the theory here is just saying, what if you made h infinitely small, depending on wherever x starting point? We started at 2. You didn't have to start at 2. Start anywhere else. This is called first principles. 17a is about using this formula or understanding to find the gradient manually. Okay, the long way to do it. If you don't get that, you can move on. Okay, 17b is that you do shortcuts. It just means you have to learn shortcuts all the way. But that's where it all began. Okay, so this is the very beginning of everything about calculus. You can understand. Okay? I'm going to stop the video. It's very untimely.